Okay, folks, we're back. I'm just coming from around the camera here. We have a bonus today. As I think I may have mentioned before, I kind of set up this little teaching studio here at my church, and the organist comes in the mornings to rehearse on the organ, so you may hear some background organ music. So hopefully it's not too distracting. It might actually be kind of pleasant, depending if you like organ music. If not, my apologies. Okay, so this is just a quick one, I hope. So at this point we've covered a ton of stuff. We're going to really switch into calculations mode at this point. So LeChat's principle is really one of the foundational ideas in equilibrium. The idea that an equilibrium tries to maintain itself. We're going to see that theme over and over again. And then an equilibrium will shift to the right towards the products, or shift to the left towards the reactants, in order to maintain an equilibrium level of concentrations or pressures, depending on what it is we're measuring. Okay, so that is a foundational principle. Now, we already visited that, did that topic mathematically when we did those Q calculations. So, if you have Q is less than K, it goes to the right. If Q equals K, then you are at equilibrium. And if Q is greater than K, then it shifts to the left. So we've already done that mathematically, and that's fine. But we want to make sure we don't just memorize algorithms here. We want to make sure that you understand why these things happen. So in your homework, it's not labeled LeChat's principle. I'm just going to kind of take a look here. So we're in problem set number 2, I think. And let me see here. Oh, by the way, I've got the Zoom office hours going on, so I may have to chime into that. So we've done, you've done problem set number 1, should be pretty set. Problem set number 2, 1 through 3 should be done. So this is really, and I have it up here, problem sets number 2, number 4 through 7. I'm not going to do all of those with you, but I'm going to take you through kind of a comprehensive example. And I hope you can see this okay. I know the sun was shining on this one. So this is P4. This is number 5 from the homework. And when I say it's a bonus version here, but if you want to stop the video and copy all this down, that's fine. Okay, so we're going to do all the stresses. So let's talk about before we get to all these, what can we do to a chemical equilibrium to change it, and then what would it do to change back? Now, textbooks often call those as you're stressing the equilibrium, you're putting a stress on it, you're changing it, you're applying some kind of external force if you want to think about physics, and we'll get to all that. Okay, so here's the chemical equilibrium. It's a homogeneous equilibrium because everything's a gas, so there's nothing we can ignore here. And it's exothermic. So we can have you calculate the enthalpy. You go to the tables, take 4 times the heat of formation of the phosphorus trihydride minus the sums of these 6 times. Okay, so you might remember doing that from the tables in the back of the book or the information you were given last semester. We're going to do things similar to that. So you're given that it's exothermic. So what that really means is that heat is a product. We don't normally do that because it's not something we balance, but there's heat over here. Maybe I'll just do it like that. If it's endothermic, we put the heat over here. Okay. So let's think about this a little bit. Just think what's actually going on here. You have a molecule of P4 reacting with 6 molecules of diatomic hydrogen to produce 4 molecules of phosphorus trihydride. Okay, if you want to think about it, it's like 7 gas molecules, so 1 plus 6. So remember how we had to add up the moles of gas in that last problem? We're not going to do that here. This is qualitative. It actually makes a lot of sense. So if you want to think about it, 1 molecule plus 6, you have 7 gas molecules turning into 4 gas molecules. I was going to do the cartoon pictures, you know, like showing that, for like doing 6 of those. It just doesn't, I didn't think the cartoon pictures would really help out here. So basically, you have more gas over here than you do here. If you want to think about it, this is sort of like your high pressure and low pressure. So in terms of gas pressure, the reactant side has more pressure than the product side. That actually matters for equilibrium. Okay, let's go through this here. So typically when we think about an equilibrium, we try to think of some industrial process like ammonia. I don't want to keep using ammonia. I think one of the problems might use ammonia. Oh, by the way, there's one of your homework problems where it's the same pressure on both sides. And that's actually an interesting problem where you have the same gaseous pressure. Okay, so I'm just going to kind of talk you through this rather than writing down answers for all this stuff. So if you want to write down the notes or just I'll ask you to make a prediction. Okay. So again, typically with a problem like this, our goal is to maximize some product that's being made. That's a typical kind of problem. You want to produce as much pH3 as possible. So what would you do to make that happen? Okay, so you want to push the equilibrium as far to the right as you can. So any stress that pushes it to the right. Okay, but let's go through actually all of the stresses. And then we can figure out which ones would actually push it to the right, which ones would do the opposite of what we want to do, push it to the left. So I'm just going to kind of talk this through, and you might want to write it down. Okay, so what I have here is really a comprehensive list of all the things that you can do to an equilibrium to change it. And then it will respond, because that's the LeChat's principle. So the first thing you can do is add or remove reactants or products. So for example, a pretty typical thing to do to maximize how much something is produced is, as it's produced, you remove it. So let me give you the first part of this problem. What would the effect be if you removed pH3? Well, if you remove pH3, the equilibrium is going to shift to the right in order to replace that pH3. Well, what does that mean? That means that the H2 and the P4 will go down because it's shifting right. The opposite would be true. What if, for whatever reason, we pumped in a bunch more pH3 from another resource? Well, it's going to shift to the left to bring it back down to equilibrium. So you would produce more of the reactants and reduce this back down. So that's adding or removing, and we can do all kinds of things here. What if I remove hydrogen using some other process? I don't know what that would be. If you remove hydrogen, the reaction's going to shift left to replace it. If I add phosphorus, it's going to shift to the right to get rid of that excess phosphorus. So think about that. The effects of adding or removing any products and which direction that would go. So remember, the whole point is to keep the equilibrium concentrations there. So that would be one stress, and I forget exactly which ones I asked in number 5, but make sure you go through those. Okay, another thing I can do is I can heat up a reaction or I can cool it down. That means I increase the temperature or I decrease the temperature. What does that mean in terms of the reaction? That means I'm going to add heat. I'm physically going to, I'm doing this as I'm cranking up your hot plate. Or I have some vessel where I change the temperature. So I'm adding heat. Or cooling means to remove heat. So think about heat as a reactant or a product. So in this case, if I add heat, I raise the temperature. That means that I'm putting in a product. So I'm adding heat. Well, the reaction is going to shift to the left in order for that, if you add heat, because it's one that wants to get rid of that heat. This is true for exothermic reactions. If it's exothermic and you heat the reaction, it drives the equilibrium to the left. Typically for an exothermic reaction, you want to cool it to drive it to the right. So if I cool it and take this heat down, the equilibrium is going to shift to the right to replace that heat and push the equilibrium typically in the direction we want, to the right, towards the product we're trying to make. So that's the effect of temperature. The last one, which is kind of a little strange to figure out, is changing the pressure. How do you change the pressure? Well, you have a container and you make the container smaller, or you take it from a big container to a small container. So if I take it from a 1 liter to a ½ liter, I just double the pressure because there's more collisions going on. Or if I go from a ½ liter to a 5 liter, I just really decrease the pressure because now there's fewer collisions going on. So the size of the reaction vessel can change the pressure. Make the reaction vessel bigger, the pressure goes down. Make the reaction vessel smaller, the pressure goes up. And that's kind of what I put here. Is how can you do that? There's other ways to do it, like you could pump in another gas like helium that doesn't react. But if I pump in a bunch of helium gas, it'll increase the pressure. Okay. Or I take the air and I jack up the air pressure. That's fine. But the bottom line is, what does changing the pressure either up or down, again, you change the pressure down by increasing the volume, you increase the pressure by decreasing the volume, that's a gas law thing, don't worry about that. Well, what's that going to do to this equilibrium? Well, if I increase the pressure on this system, this whole system here, and the pressure goes up on the whole thing, LeChat's principle says that the equilibrium is going to shift so that the pressure goes down to counterbalance that. Well, what does that mean? Well, that means it's going to go to the side of the reaction that has lower pressure. So this is going to be a shift right to low pressure side of the reaction. Now if I flip this around, if there was 4 and 7, this would be the exact opposite. It would shift left. But the low pressure here, because there's only 4 gas molecules and 7 gas, this is the low pressure side. So if I increase the pressure on this whole thing, it's going to produce more pH3. So if our goal is to produce more pH3, we want to do that in a pretty small vessel, or increase the pressure some other way. Similarly, I think you see where we're going. What if I decrease the pressure by making it a larger volume? Well, the exact opposite is going to happen. It's going to go to the high pressure side. So that's going to be a shift left to high pressure side. So I'll smooth that up. So in this case, the low pressure side of the products, the high pressure side of the reactants. Now that's just for this example. You'd have to actually look at these on a case-by-case basis. Which one is the high pressure, which one's the low pressure. It won't always be products and reactants. Sometimes it'll be the exact opposite. And go through your analysis. If it's exothermic, cool. Cool it, it goes that way. Heat it, it goes that way. If it's endothermic, it's the exact opposite. Adding and removing reactants and products is basically the same for any reaction. You remove a product, it shifts to the right. You remove a reactant, it shifts to the left. You add a reactant, it shifts to the right. You add a product, it shifts to the left. You want to just kind of piece all this together. I may actually ask you for a quiz or a test to kind of write a comprehensive case study based on one of your homework problems. And I think that's it. So that should let you do these problems and look in your book. I forget which section LeChat's principle is, but it should be easy to find. And let me know if you have any questions. Again, we're going to bow out of this video.